Welcome you all to Alpha and Omega Mathematics by Vijaya Jackson. Let us see the topic group theory, the definition of group. After that, we are going to see about the topic properties of a group. Let us see the definition of a group. So, for defining a group, so we need a non-empty set. A non-empty set having the binary operation star. We are taking the binary operation star. So if G is a non-empty set, is a binary star is a binary operation of G, then so it is algebraic system G comma star is called a group if the following conditions are satisfied. 4 conditions. What are the 4 conditions? So first one is a closed property, second one is associative property, third is identity property, fourth one is a inverse property. So closed property. So what is closed property? See here, for all A comma B belongs to G, then A star B belongs to G. So just take it 2 elements from capital G. So find out the multiplication or addition of A and B. So again check the answer. That answer is belongs to capital G. We can say that closed property holds. The second property is associative property. For all A comma B comma C belongs to G, then we are defining that A star B star C equal to A star B star C. So it is associative property. Third property is identity property. Identity always we denote it as by small e. So here just to take it one element A belongs to capital G. So find out A star E. That answer is equal to A means you can say that E is the identity of the particular group G. So for example, so you can take Z is a set of all integers. So set is equal to so minus infinity to plus infinity. Set contain the elements are minus infinity to infinity. So here see here 0 is the identity of this particular group. So how we are saying that 0 is the identity element? So see here, if you are taking element 1 means 1 plus 0. 1 plus 0 we are getting 1. 2 plus 0 is we are getting 2. So under addition, in Z 0 is the identity element. So likewise we are defining the identity property. So then inverse property. So inverse property is A into A inverse is equal to E. A into A inverse. So how see here? So for all A belongs to G, there exists an element A inverse belongs to G such that A star A inverse is equal to A inverse star A equal to E. So this way we are defining existence of inverse. So if any one of the non-empty sets satisfies these 4 properties, we can say that it is a group under the binary operation star or under the binary operation addition, under the binary operation multiplication, like that we can define it. So in general, we are taking the binary operation as star. So see the example, Z comma plus is a group under addition. Set is set of all integers. It is a set of all integers. Under addition, it is a group. So after that, we have one more property. The property is commutative group. So what is commutative group? Commutative property says, so suppose 2 elements belongs to capital G, A comma B belongs to capital G, then A star B equal to B star A. So if we get A star B equal to B star A, then we can say that commutative property holds. So suppose one non-empty set is there, so it satisfies all the 5 properties, then we can say that it is a commutative group. Another name is abelian group. You can say another name is it is an abelian group. So this way we are defining a group. So set of all integers is a group under addition. So the next definition, see here, order of a group. Order of a group, the number of elements in a particular group. The number of elements in a particular group is called the order of a group. So see here, when G is finite, the number of elements of G is called the order of G. We denote it by order of G are like this simple order of G. Order of G meaning is the number of elements in capital G. So for example, so H is equal to or G is equal to 1, 2, 3, 4. This is a non-empty set. Okay. So here order of this G is 4 because G contains the elements or numbers, 4 elements are there. So therefore we are saying that order of G equal to 4. So like that we are defining order of a group. So order of a group meaning is the number of elements in G. So next we can calculate it order of an element. Order of an element, see here, if the element A belongs to G where G is a group with identity element E, then the least positive integer M for then the least positive integer M which A power M equal to E is called an order of an element. So order of a group we can calculate it. So order of each element also we can find it. So this is a definition of a group. So after that order of a group, order of an element. Let us see the properties of a group. So properties, see here, the first property says the identity element of a group is unique. The identity element of a group is unique. So see here, so one set is there, one non-empty set. So we can define it whether it is a group or not. So by checking all the 4 properties. So what are the properties? Closure, associative, identity, inverse. So then this here, this group G is having the identity element. If it has the identity element means it is unique. Unique means there is only one identity element of the particular group. So this is the first property. So we are going to see about the proof of the first property. So see here how we are going to prove it. Look at this. So here we are proving it is unique. Identity element is unique. So we are going to consider it. Suppose there are 2 identity elements in the particular group. There are 2 identity elements in the particular group. So we are going to prove that if it has 2 identity element means it is same. It is same. This way we are going to prove it. So see here, suppose E and E dash we are taking. If possible, let there be 2 identity elements in the group G comma star, say E1 and E2. Yes, E1 and E2 we have taken. There are 2 identity elements. We are going to prove it. E1 is equal to E2. Both are same only. We are going to prove like that. So suppose E2 is an identity element. E1 may be any one of the element in G. Then identity property, by using identity property, we can write it E2 star E1 is equal to again E1. So identity property says 1 plus 0 is equal to 1, 2 plus 0 is equal to 2, like that. So E2 is the identity element now. E1, it is another element. Therefore, taking under binary operation, E2 star E1 is equal to E1. Take it as equation number 1. So again, E1 is also we have considered it is an identity. So since E1 is an identity and E2 belongs to G, then we are writing that by using the identity property, E1 star E2 equal to again E2. So see here, combining 1 and 2 both are same only. Therefore E1 equal to E2. We can equate it. E1 equal to E2. We have considered there are 2 identity elements in the particular group, but we have proved if it has, then it is equal. E1 and E2 are equal. So hence we can conclude it. The identity element of a group is unique. So this way we are proving the first property. So let us see the second property. The second property is the inverse of each element of G comma star is unique. So here also the inverse of each element, the previous property says the identity element of entire group. The identity element of entire group is unique. But here the inverse of each element is unique. So because in a group G, we can find the inverse of each element. We can find the inverse of each element. So for example, set of all integers under addition, it is a group. So here 0 is the identity of Z, and also here inverse. For example, 1 the inverse of 1 is minus 1. How the inverse of 1 is minus 1? 1 minus 1 is equal to 0. Again, inverse of 2 is minus 2. So here 2 minus 2 only we are getting 0. 3 minus 3 it is 0. So inverse of each element we can find it. So here the property says the inverse of each element of G comma star is unique. Suppose one element is having inverse means it is a unique one, inverse only. There are more no inverse of the particular element. So this is also we are going to prove in contradictory way. So if possible, see here, if possible, let B and C be two inverses of the element A belongs to G. So we have taken one element from capital G, that element is small a. So small a has here small a as identity and also it has an inverse. So A belongs to G. So here there are two possible inverse elements of A. Suppose B here. Suppose B is the inverse of A means by the definition of inverse property, we can write it A star B equal to B star A equal to E. So by you applying inverse property. So again we have considered C is also the inverse of capital G. By using inverse property, we can write it here A star C equal to C star A equal to E also. So by combining C here, this is also E, here also E, we have taken B equal to, we are going to prove B equal to C. So consider B answer. B can be written as E star B. E is the identity element. So multiplying B with the E, we get the same answer B. Therefore, we can write it B is equal to E star B. So again E, we can put it E by here C star A. From second equation, we can put it E by C star A. So C star A star B. So again, it is a group. So therefore, G is satisfies associative property. So associative property holds. Therefore, we can change the bracket. So C star A star B. So again, see here by using the equation 1, the previous equation 1, A star B, we can put it by it is small e. So here C star E. So C star E is nothing but it is C because E is the identity element. So we have proved now B is equal to C. So we have considered in the beginning B and C are two inverses of the element A belongs to capital G. But now we have proved B and C are equal, both are same only. Hence we are concluding that the inverse of an element of G comma star is unique. So see here one note, group has only one inverse. Group has only one inverse of each element. So the next property, see here, it is a cancellation law. So property 3, the cancellation laws are true in a group. So see here left cancellation law and right cancellation law. A star B equal to A star C implies B equal to C. So here you can't put it, we can't cancel it directly, immediately. So by using some procedure only, we are cancelling. So this is called cancellation law. The next cancellation law is B star A equal to C star A. So this implies B equal to C. So see here how we are going to prove it. So the first one, A star B equal to A star C implies B equal to C. It is called left cancellation law. To take it A star B equal to A star C. So both side we are pre-multiplying by A inverse. So pre-multiplying A inverse on both sides. So see here what we get. A inverse star A star B equal to A inverse star A star C. So here again G is a group. Associative property holds. Therefore A inverse star A star B equal to, we can interchange the brackets. So again A inverse star A is, what is A inverse star A? It is E because G is a group. So G satisfies inverse property. So A inverse star A becomes E. So E star B equal to E star C. So this becomes, we are getting B equal to C. So this way we are proving that left cancellation law. So similarly, we can prove that right cancellation law. So see here, we are considering B star A equal to C star A. We are going to prove it now, B equal to C. So here, So you are post multiplying A inverse on both sides. So see here B star A inverse is equal to C star A inverse. So multiply it B star A inverse. So because it is associative, G is associative, that's why we are interchanging the bracket. So again A star A inverse becomes E because G is a group, inverse property holds. Therefore, B star E equal to C star E. So this becomes B equal to C. So this way we are proving that left cancellation law and right cancellation law. So now the next property, property 4, B inverse star A inverse is the inverse of A star B. So that is, the property says A star B the whole inverse is equal to B inverse star A inverse. So here A star B the whole inverse, immediately you will write it B A inverse star B inverse, but we can't write it like that. A star B the whole inverse is equal to B inverse star A inverse. So this is the property 4. So see here how we are going to prove it. Consider A star B inverse star A inverse. Because we are proving now B inverse star A inverse is the inverse of A star B. Therefore, we are considering A star B inverse star A inverse. So again, so here the elements are from capital G, A and B belongs to capital G. So therefore, we are rewriting A star B inverse star A inverse. So this is equal to A star E star A inverse. Again, this is equal to A star A inverse, which is equal to E. So similarly, B inverse star A inverse star A star B. So left side also just to take it. So this is equal to B inverse star A inverse star A star B. So again A inverse star B becomes, it is E. So B inverse star E star B. So here we are getting the answer is E. Both sides, left side and right side, we are getting the answer is the identity element E. Therefore, we are concluding that B inverse star A inverse is the inverse of A star B. Otherwise, we can write it like that. A star B the whole inverse is equal to B inverse star A inverse. So it is the fourth property of a group. So now the fifth property. If A comma B belongs to G, if A comma B belongs to G, the equation A star X is equal to B has the unique solution X equal to A inverse star B. So similarly, the equation A star Y has the unique solution Y equal to B star A inverse. See here. So we are proving the first part. If A comma B belongs to G, the equation A star X equal to B. Here one equation is there, A star X equal to B. They have found a solution. The solution of this equation is X equal to A inverse star B. So they have found the solution is X equal to A inverse star B. The proof is actually what we are going to prove it. This solution is unique. Only one solution we are having. There is no more solutions of this equation A star X is equal to B. So this is only we are going to prove it. So one equation is there. A star X is equal to B. So the solution of this equation is X equal to actually. So just taking A into left side. We are getting the answer is X equal to B star A, actually A inverse star B. So X equal to A inverse star B. Similarly, the equation A star Y has the unique solution Y equal to B star A inverse. So see here how we are going to prove it. The solution is unique. We are proving the solution is unique. So let's see be the solution of this equation X equal to A inverse star B. So again one more solution if we have. D is the another solution of the same equation X equal to yes, A star X is equal to B means we are going to prove that C and D are same. Both are same. C and D are unique. We are going to prove it like that. So just to consider A star C. This is equal to A star A inverse star B. So here this is equal C. Here C places. So just to put it A inverse star B. This is one solution. So now here G is a group. Therefore we are taking the associative property. So A star A inverse star B is equal to E star B. So this answer is equal to B. So just to take it, the A star C answer we have calculated, it is B. So if possible, another solution, x equal to dB, another solution of the equation A star x is equal to B. Then definitely D satisfies here the same equation. So putting x in the place B, so you are getting A star D is equal to B. Yes, we are going to prove now D equal to C. So just to take it considering A star C, this is equal to D only. So again this is equal to A star D. So therefore, so we have proved A star C equal to A star D by using cancellation law. So here we are proving that C equal to D. A and getting cancelled. So we have considered there are two possible solutions of the equation A star x is equal to B. But we have proved C and D are same, the same answer, solution only. Therefore, the solution of this particular property, this equation is unique. The solution of this equation A star x equal to B is unique. So similarly, we can prove the second part also. This equation A star y equal to has the unique solution y equal to B star A inverse. So here also we can prove it the same procedure. So now the property sixth property, see here, G comma star cannot have an idempotent element except the identity element. So see here, G comma star is a group. We have considered one group under the binary operation star. So it is a group means there are four property holes, right? So what are the properties? So closure, associative property, identity, and inverse property holds. So G comma star holds all the four properties. Suppose in the set, if we are able to find an idempotent element, then that idempotent element is an identity element only. It is an identity element. So idempotent element and identity element both are same. That is only the property 6. So idempotent element and identity element are same. That is not a separate element. So what is the definition of idempotent? Idempotent property says A star A equal to A. A star A equal to A or A square equal to A. A star A inverse is A star A equal to A, or you can write it A square equal to A. So this is idempotent. If you are able to find this element, we are going to prove that now A equal to E only. A equal to E. So see here, we have taken A is the idempotent element, E is the identity element. Now we are going to prove it the same, the identity element and the idempotent element are same. So just to consider, see here, consider E equal to A star A inverse. You can write it like that is E is the identity. By using the identity inverse property, E equal to A star A inverse. So this is equal to E can be written as E is A star this A. This A we have written A by equation 1 A star A. A star A equal to A inverse. So this is equal to A star A inverse by using associative property. Again put it A star A inverse is equal to E. So again A star E only we are getting. A star A is, what is A star E? So it is again E, multiplying E with A. So you get the answer is A only. So you have taken in the left hand side, it is E. So here the answer is A. So hence we have proved the idempotent element of G is the identity element. So one group is there means one group is there. So we can prove it. Idempotent element and identity element are same. Both are same only. So see here, this class, so you have studied about what is the definition of your group. The definition of your group, what is the definition of your group? So you are just considering a non-empty set. Here under the binary operation star, it satisfies four properties. The properties are closure property, associative property, identity element, and inverse. So any one of the non-empty sets satisfies these four properties. We can conclude that it is a group under the binary operation star. It may be addition or multiplication, anything. So another definition is commutative group. Commutative group is A star B is equal to B star A. So suppose there are two elements from capital G. So then it satisfies A star B equal to B star A. We can say that it is a commutative group. So 5 conditions satisfied means we say that it is a commutative group, or another name is abelian group we have studied. Then order of a group, order of a group. After that, order of an element we have discussed. Then we discussed about the properties of a group. The properties of a group. So the first two properties are very important. Properties, the first properties is here identity element of the entire group is unique. Identity element of the entire group is unique. So here the second property is inverse of each element is unique. Inverse of each element is unique. That is the difference. So in the first property, the entire group, we have only one identity element. But in the second property says each element we have unique inverse. So all the properties we have discussed. So just to go through it, all the best for your studies.